In this video, I'm going to quickly discuss titrations. And so in this lab, we will be titrating using a strong base and a weak acid. And the weak acid will be KHP. And so in this lab, we will be using a burette for our titration. And so that's what this thing is here. And so this is used to deposit small amounts of our strong base into a solution of the acid. And so what we're essentially going to be doing in this lab is what's called a standardization. And so we know the concentration of the weak acid, but we aren't exactly sure about the concentration of the strong base. And that's because the NaOH in its solid form can actually absorb moisture from the air, which will actually increase its mass, and so that will give us an inaccurate concentration when we dissolve it in water. And so we can use this to actually standardize and find the concentration of our NaOH in solution. And so to do this, we will be using a pH meter, and so that is this. And so as of recording this video, I actually don't know what the pH meters in our lab exactly look like, but pH meters are all fairly similar, and so they all have a design that's kind of like this. So we have our screen here that actually shows the pH, and it will show it at a particular temperature. And then we have our electrode here, which actually goes into our solution, and that will read off the pH of the solution. And so we want to try and make sure that the electrode isn't touching the sides of the beaker here, because that can actually give us an inaccurate reading, because the electrode is just that, an electrode. It's actually looking at the sort of well, it's I'm not going to get too much into it, but it's looking at the sort of the voltage, I guess, of the solution here, or the ionic strength of the solution here, where the H plus ion is the ion that we're concerned with. But anyway, I don't want to go too far down that rabbit hole. The thing that's important here is that the pH meter measures our pH, and we can measure that up to 2 places after the decimal on a normal pH meter. And then, so the burette, also, it's important to know that we can actually go 2 places after the decimal on the volume on that. So we can add up to we can add something like 1.00 milliliters at a time, or we could have 1.01 milliliters at a time. And so with a burette, we can actually determine the difference, this much of a difference in the volume that we add. All right, and so a titration curve is going to look like this. So you will be obtaining data. So you'll add a little bit with the burette. You'll wait for the pH meter to stabilize on a pH as you're mixing the solution to make sure that the added NaOH gets homogenized and mixed into the solution. And then you will write down the pH after these certain amounts of volume are added. So the after volume of NaOH is added, and so then you will plot that as pH like this, and so you'll end up with a curve that looks like this. And so the 2 points to kind of pay attention to are this right here, this halfway point, and so that is when the concentration of our acid is equal to the concentration of the conjugate base. And so we have the acid, and so in our case it will be the KHP, and so the protonated form of it will be equal to the deprotonated form of it here at this halfway point. Then we have this equivalence point, which is actually when the concentration of the acid plus the conjugate base. So we could say HA plus A. So the concentration of that is equal to the concentration of our base that we're adding. So that would be the NaOH. And so that's the equivalence point there. And so the thing to notice is at the halfway point, when we're using the Henderson-Hasselbalch equation here, we will have equal amounts of this conjugate base and this acid here. And so this will be the log of 1, which is just equal to 0. And so that goes away, and we have pH is equal to the pKa at that halfway point there. All right, and so some of the math that we're going to have to be using in this lab, in the post lab for this. So we have our reaction here. We have our acid. We add that to H2O. That becomes the conjugate base plus this H3O plus. And so then the equilibrium for that is the Ka, which is equal to the our acid, or the conjugate base of our acid here, multiplied by the H3O plus concentration. That is over the HA here. So remember, we could add the H2O here, but that will just be 1, so we remove that and we end up with this. And so the pKa, which is a measure of the strength of the acid, is the negative log of the Ka, which is our equilibrium constant. And so we see that the larger this Ka, the lower our pKa, because we are taking the negative log here. And so when we have these smaller pKa's, that means that we have a stronger acid. And we're also going to be using this pH is equal to the negative log of the concentration of H3O plus right here. And so once again, the lower the pH, the more concentrated the H3O plus is, and so the more acidic our solution is. And so that is kind of an important distinction too, is that the pKa is essentially the sort of strength of the acid, is the propensity of that acid to lose its H plus ion, where pH is a measure of the concentration of the acid. So pH has to do with concentration, where pKa kind of has to do with sort of, for lack of a better word, the intrinsic strength of the acid. So pKa is not dependent on the actual concentration of the acid, where pH is dependent on the concentration of the acid. And so with the pH, if we want to get back to the concentration of our acid, we just do 10 to the negative pH power here, where we could do the same thing here with our pKa. If we want to get back to the Ka, that will be 10 to the negative pKa right there. And so these are kind of this is kind of the math that you use to sort of manipulate these Kas and pKas and pHs and concentrations of acid and so forth. One other thing to know is that in our post lab, we will have to be finding the concentration of the NaOH, because remember, we're doing a sort of standardization experiment here, and so we have to know the mass of the KHP that we're actually putting in there, and then we have to know the volume of NaOH solution that we are titrating into the KHP. Because if we know the mass of the KHP and then we know the volume, we know the volume of KHP solution, we can actually use this to find the actual molarity, the actual concentration of the NaOH. And so for that, we can use essentially the mass of the KHP P times the molar mass of KHP times molar the molar ratio of KHP to NaOH, and then we can sort of divide that. We can divide that by the volume of the NaOH that we have added. And then from this, we can find the actual concentration of the NaOH. But anyway, like I said, in this experiment, we'll be doing a titration, looking at the pH. Using a pH meter, we will then be graphing that on a titration curve that looks like this, where the volume of NaOH added is on the x-axis, and then the pH that we measure for each one will be on the y-axis. And then from this, we can find the the various things that we want to be looking for, such as the pKa and the concentration of the NaOH and things like that. But anyway, I hope you found this video helpful, and I will see you later.